So good morning everyone. Today we are going to discuss distribution functions with the help of some examples. So in the previous lecture we discussed the distribution function, its definition and some of its properties which are used to determine whether a given function is a distribution function or not. So today I am taking the first example. Suppose x is an indicator random variable for an event A. So we write it as xia, where and probability of A is defined as P and probability of A complement is defined as 1 minus P. So since x is an indicator random variable, so it will take only two possible values, which is 0 and 1. So we will write x of I. So x will be taking the value as 0 with probability 1 minus p and value 1 with probability p. So the distribution function, which is f of x and x, will be written, and it will have three components for x less than 0. So we see here that x cannot take value less than 0. So distribution function is defined as 0 for that range. Now, as x equals 0 but is less than 1, so the probability is 1 minus p. Okay, and if x exceeds 1, then what happens? Let's see. It is 1 minus p is the probability of x is 0 plus probability x is 1. So this comes out to be 1. So if I want to plot this distribution function, now it will have two jumps. At x is equal to 0, we are given that probability is 1 minus p. It will be probability 1 minus p. So this distribution will continue till a point where x is equal to 1 is observed. So at x is equal to 1, this probability is approaching 1. So I will write this. For all x greater than 1, this probability will be 1. Here we are writing f of x, and this is denoting x. So this is the quantum of jump of p at x is equal to 1. So this is the jump. So this is the way we write the distribution function of an indicator random variable. Now let's move to some another example. Suppose x is a degenerate random variable. So what is the property of degenerate random variable? Suppose x is defined as random variable. So what in a for a degenerate random variable, x is allowed to have only one possible value. Say that particular value of x is c. So its distribution is given as probability of x is equal to c is equal to 1. So this is the case, and if this is the scenario, then how we will write the distribution function of a degenerate random variable? We will write as probability of xx is given as, for all x less than 0, less than c, we would say distribution function is 0 because it is defined only for a point x is equal to c, and it will be 1 once the value of x is has attained the value of c. So in this case, if you were try to plot the distribution, say I'm assuming that x is c, this is the point. So the distribution function will be, this is f of xx, and this is going to say 0 and 1. So at x is equal to c, from this points onwards, this distribution function is 1, and this is the probability 1. So at x is equal to c, the jump is 1. So this is the way to write the distribution function. Now I will write the distribution function for a random variable where we define x is the number of heads in throw of a dice 3 times. Okay. So let x is the number of heads in throwing a coin thrice. So let's write the whole sample space for this case. So since I am defining here the x is the number of heads, to start with I will be having least value of 0. So I presume that all the no heads is assumed. Now I will take x is equal to 1, so at one head is appearing. Now I will rotate this on all possible places. Now there will be only one possibility, that only head, and head is attained. So this is our sample space. Okay. Now I am writing the corresponding values of x. So here we know that x is 0. Here x is 1. Here also x is 1. Here also x is 1. Now in this case x is 2. X is 2. And here also x is 2. Here x is the 3. Obtaining the, so now I will write the corresponding probabilities. So the probability of x is equal to 0 will be, only one case is there, so 1 by 8. Now probability of x is equal to 1 will be 3 by 8, and probability of x is equal to 2 will also be 3 by 8, and finally the probability of x is equal to 3 is 1 by 8. So we have obtained the distribution of x. Now we will write the corresponding distribution function f of x of x. So how would it look like? For all x less than 0, we know that it is 0. For x, once it attains the value 1, but 0 and less than 1, so whenever x is lying between 0 and 1 and attaining the value of 0, this probability is 1 by 8. Okay. Similarly, for x is attaining the value 1 and is less than 2. Okay. So here we get probability is 1 by 8 plus 3 by 8. We got 4 by 8. And for x attaining the value 2 but is less than 3, we get the value of 1 by 8 plus 3 by 8 plus 3 by 8. It will be 1 by 8 plus 3 by 8 plus 3 by 8. So it will be 7 by 8. Now for x exceeding the value greater than equal to 3, then we will have the whole sample space. So f of x is now defined as this. So this was another example from V.K. Rohatgi, and hope you can jot it down. Now let us take an example from Tanjit Das notes. This question says check whether the following function is a distribution function, and the function is defined as f of x as 0 for all x less than 0 is x for x lying between and 1 for x greater than or equal to half. So what are the essential properties? First property I will check whether f of x at minus infinity is 0. Since we are given that f of x is 0 for all 0, so this property is satisfied. Second property says f of x at plus infinity should be 1. So here for all x greater than equal to 1, so we are given that f of x is 1. So these are the two properties which are being satisfied. The third property says fx should be increasing. So we see that f of x as 0 was 0 is 0 and f of x at 1 by 2 is, so I'm taking all lesser values, say, so it will be f of x 1 minus 2 and f of x at 2 we are given that it is 1 by 2, it is given as 1. So we see that it is fx is taking the values which are increasing from 0, 1 by 2 and 1. So we conclude that f of x is an increasing function. Now to check the right continuity, which is our fourth property. So now we check at f is at 0. We are given at f at 0 is we are given. It will be 0. So f at 0 plus h, where limit h tends to 0. The function will lie between 0 and 1 by 2. This is the function. So x plus h limit s tends to 0 and x is 0, so it is also 0. So f at 0 is right continuous. And similarly at f at 1 by 2 we are given as f at 1 by 2 we are given that 1, and also f at 1 by 2 plus h limit s tends to 0, it is also 1. So we know that we see that f of x at x is equal to 1 by 2 is right continuous. So this way we have established that the given distribution function is right continuous and satisfying all the properties of distribution function. So we conclude that f(x) is a distribution function. So another example is if if a die is rolled twice and we are defining a distribution, say random variable y, as the absolute difference in face value of first and second row growth. So y is saying that y is defined as difference between x1 minus x2, where x1 is the face value at first row and x2 is the face value at second row. So let's write first. I'm going to write the whole sample space, and then we will take the corresponding values and we will assign the value of y corresponding to each observed. So these are the sample points. Similarly, 6-1, 6-2, 6-3, 6-4, 6-5 and 6-6. So from here we observe that what are the possible values of 5? Say it is 0, 1, 2, 3, 4 and 5. Because since x1 can have values from 1 to 6 and similarly x2 has the value of 1 to 6, so we will be correspondingly we will be getting the values of this. Okay, so what will be the probability of y is equal to 0? So in this case x1 and x2 should be equal, so in this case we will get 1 1 corresponding to this a0 we will be having 1 1 2 2 3 3 4 4 5 5 and 6 6. So here we get only 6 out of 36 cases. Okay. So these points are gone. Now, what will be the probability of y is equal to 1? It will be I'm writing as a1, so it will be 1 2 2 1, then 2 3 and 3 2 and 3 4 4 3 4 5 5 4 and 5 6 and 6 and 5. So we got 10 sample points from this, and 10 by 36 is the corresponding probability. So similarly, we will write A2. The difference should be 2. So it will be corresponding to 1 3 1 and 3 and 1 and 2 and 4 and 4 and 2 and 3 and 5 and 5 and 3 and 4 and 6, 6 and 4. So here we are getting the difference of 2. So how many sample points are there? 1, 2, 3, 4, 5, 6, 7, 8. So probability of y is equal to 2 is 8 by 36. Now probability of y is equal to 3. So we see that what is the difference between, so here it is A3, the difference should be 1 4 4 1. Similarly 2 and 5, 5 and 2. Three and 6 and 6 and 3. So we got 1, 2, 3, 4, 5, 6 points here. It is 6 by 36. So probability of y is equal to 4 means the difference is 4. So corresponding to A4, you will get the value of 1 and 5. Similarly 5, 4, 5 and 1. With 2 and 6, 6 and 2. So these are the possible values for y to have the value 4. So now we got 4 cases. Now what will be the value for a is equal to y is equal to 5? Y is equal to 5, only one case will be there, 1 and 6 and 6 and 1. Okay, so this probability is 2 by 36. So this is the way how we write the distribution of x of y, and then we are going to write the distribution function for this random variable. So I am now rubbing, you can note down. Now corresponding to this y, I am going to write the distribution function. So we know that y is taking value from 0 to 5. So I will be writing of f of y For y less than 0, we know that probability is 0. For y is having the value 0 and less than 1, so it is 6 by 36. And then we accordingly we will enhancing the values of y. For this value we will be writing y is greater than y is less than 1 and 0, so this will be probability of 6 by 36 plus 10 by 36, so it will be 16 by 36. So y is taking, if we take the value y but is less than 3, so we are given that 16 by 36 plus y is taking the value of 2 is 8 by 36. So it is 24 by 36. Now if y takes the value say 3 but is less than 4, so we will add 1 by 6 by 24 by 36 and we enhance the probability by y is equal to 6 by 36, so it comes out to be 30 by 36. Now similarly, if y takes the value of 4 but is less than 5, so for this we will add 4 more to this probability, 30 by 36 plus 4 by 36, so it will be 34 by 36. And for y greater than equal to 5, so 34 by 36 plus 2 by 36. So this comes out to be 36 by 36, which is nothing but it is 1. So this is the distribution function of y. So this is the way we write the distribution function. Now I will be taking, I will be giving you some examples where I will check whether a given function is a distribution function or not. You can note down if you wish to. So now I will be doing some example. Say check that f of x which is defined as 1 by pi tan inverse of x for x is in the range of minus infinity to plus infinity. Okay, this is from V.K. Rohatgi. So let's check whether, first of all, we will check whether f of x at plus infinity is, first let's check at minus infinity. So it is 1 over pi tan inverse of minus infinity. So 1 over pi, and at minus in tan inverse of minus infinity is at minus pi by 2. So we see that f of x is coming out to be minus of 1 by 2. So which is less than 0. So there fxx cannot be a distribution function. Similarly, we see that f of x at plus infinity is 1 upon pi tan inverse of plus infinity, which is 1 over pi, and this is pi by 2. So this is 1 by 2. So in either case, we are not getting the property of distribution function satisfied. So f of x is not a distribution function. Now I say I take an example, and now I revise this distribution function, and now I am adding 1 by 2 to the above distribution function, and now I will check whether this function can satisfy the properties of distribution function. So answer is yes. So by adding this quantity, this half, we can convert this function as a distribution function. So let's check what is happening at f of x at minus infinity. So it is 1 upon 2 plus 1 upon pi tan inverse of minus infinity. So we get 1 upon 2 plus 1 upon pi and minus of pi by 2. So it will be 1 by 2 minus 1 by 2 is 0. So this property is satisfied by adding a constant 1 by 2. Similarly, f of x at plus infinity, we get 1 by 2 plus 1 upon pi tan inverse of plus infinity. So we get 1 by 2 plus 1 upon pi, and tan inverse of plus infinity is nothing but it is pi by 2 into pi by 2. So we cancel out this pi, so we get 1 by 2 plus 1 by 2 is equal to 1. So we know that now for the checking whether the function is increasing function, so we take f dash x, which is derivative of d over dx of 1 by 2 plus 1 upon pi tan inverse of x. So it come out to be 1 over pi 1 plus x square, which is increasing. So we say that fx is increasing function. Okay. So also fxx is continuous. So this fx satisfy fxx, which I have defined f of x as 1 by 2 plus 1 upon pi tan inverse x is a distribution function. Okay, and in fact this is the distribution function of Cauchy density. So today we have discussed the properties of distribution function from by examining whether this function of a given function is satisfying all the properties of distribution function. Answer is yes. Then we conclude that or if all the properties are satisfied, the given function is a distribution function. So there are two more examples I am going to discuss today. So this question says f of x is defined as 0 for x is less than equal to 1 and 1 minus 1 upon x for x is greater than 1. Okay. So now we have to check this distribution function. So we see that f of x at minus infinity, it is defined as 0. From here we can observe this. Also f of x at plus infinity, it is defined as 1 minus 1 upon infinity. I'm taking a limit. So this is 1. So second property is also satisfied. So now we see whether this function is increasing. So we are differentiating this distribution for this function. So this distribution this comes out to be 1 over x square. So which is always greater than 0 for all x greater than 1. So we see that f of x is increasing. So now we have to check whether it is continuous. So we see that f of x is an algebraic function which is continuous. Indeed, you can say right continuous as well. So f of x is a distribution function. So this way we have checked another distribution. Now the final example I am taking from Rohatgi. So here we have seen whether this function at minus infinity is 0, f of x is 1, derivative of fx to check whether the function is increasing. So we got that derivative as positive for all x greater than 1, and f of x is increasing function. We concluded that, and also we see that f of x, which is given by 1 over 1 is a continuous function. In fact, it is right continuous as well. So we concluded that f of x is a distribution function. So another example, here we will be taking the distribution function of an exponential family, exponential distribution, and then we will check whether this function also satisfies the conditions of being a distribution function. So let's write the distribution function of exponential distribution with parameter lambda is equal to 1. So it says f of x is 0 for x less than 0 and 1 minus e to the power minus x for x greater than equal to. So f of x at minus infinity, we are given that it is 0, and f of x at plus infinity will be 1 minus e to the power minus infinity, which is nothing but which is 1. Now to check the decreasing, it is an increasing function. So we see that f of x, which is d over dx of f of x, we see that which is e to the power minus x for x greater than 0. So f of x is also, this function is also greater than 0. So we, and also f of x is continuous. So we conclude that f of x is a distribution function. So here also we saw the properties of distribution function, and we concluded that this distribution is also a distribution function. So that's all for today, and we will be discussing more examples, and in particular I will be giving an example where a function is not defined, is not a distribution function because of the right continuity at a given point. Okay, thank you.